Hello there, this is Truth Socrates. Welcome to our 5th video in my series for multivariable calculus, also known as Math 5C in Pasadena City College. So I'm happy to say that in this video, we will be finishing with the material in this handout, Thinking in 3 Dimensions. So we will be looking at surfaces, which means that we'll be drawing a lot of pictures in GeoGebra, and we are going to look at functions of 2 variables, okay? Because after we finish with this handout, we will be looking at what are called double integrals. And for this, we will need to understand functions of 2 variables. So we will continue with spheres, which will be found at the bottom of page 24 of Thinking in 3 Dimensions. So I will see you there. All right, so everyone knows what a basketball looks like. So a sphere is basically just a generalization of a circle in 3 dimensions. So to do the algebra, we fix a point on the plane called the center of the circle. It's usually labeled as HK. And we fix a radius, R. And we want to find all the points on the plane which have the same distance, R, from the center, HK. So let me scroll down over here. And this is how we usually write the standard equation for a circle. X minus h squared plus y minus k squared is r squared, because the distance formula has an ugly square root. So if that square root is equal to r, then square both sides. You'll get r squared, and you get rid of the square root. So it's the same idea. We now fix a point in space, and that center will be labeled ABC, and we have the same radius r. And we look for all the points x, y, z in Cartesian space whose distance from the center is r. Okay, and of course, all of those points form what we call a sphere. So it's just like this equation, but we have x minus a squared plus y minus b squared plus z minus c squared equals r squared. Okay, so let's go to GeoGebra and let's make a sphere. All right, so how about let us input x plus 3. So I need a square, and you'll find that in the keyboard here. And there is the square symbol. All right, whoops, wrong place. So we have to get out of the parenthesis, and that's where we click the square. There we go. So notice that it's starting to show something here. Okay, of course, we're not yet finished. So continue. How about y minus 1 squared? Ooh, more changes in our picture. So, now we have something very interesting. And then we have plus z. How about z minus 2 quantity squared? Okay. Now it has completely disappeared. What are you doing? So let's put, how about 25? Okay, there you go. So notice, started out with 2, and when we put the 5 in, it got bigger. Okay, so of course, that is because when it was 2, the radius was square root of 2. Now that is 25, the radius is 5. Okay, where is the center? Okay, so we can read it off here. The center should be at -3, +1, +2. Okay, so let's put that in. -3, +1, +2. Ooh, there it is. That looks like it is dead center of that sphere. Okay, and is the radius 5? Let's look at it up here. Ooh, here is 2, -2. No, that's +2. And this appears to be -8, maybe. Okay, so actually the should be measuring along here. So yeah, that looks like 10 units. So the radius is 5. Okay, So yeah, there it is. And let's look at it from standard view over here. So yeah, center is at -3, -3 back here, +1 over here, +2 up here. Okay, let's make another sphere rather. Okay, bonus example. So let me take that away. Let's leave the center up there. Okay, so how would we make a sphere centered at the same point, but I want it to be tangent to, how about the YZ plane? Okay. All right. So what is the YZ plane? Okay, so those are all the points where x equals 0. Okay, so remember we talked about planes in a couple of videos ago. So we want the sphere to be tangent to this plane, the YZ plane. Okay, so what does tangent mean? It should be just kissing that plane. Okay, when you put basketball on the floor, the bottom of the basketball is tangent to the floor. Okay, so if that's the case, then what should be the radius of that sphere? Okay, well, its center is over here. So how far is the center from the YZ plane? It looks like it is controlled by the x coordinate, okay, which is -3. Okay, so therefore that distance should be 3. That's our radius, 3. So it will be the same equation. On the left, we will have x plus 3 quantity squared plus y minus 1 quantity squared plus z minus 2 quantity squared equals, we said the radius is 3, so right side should be a 9. Aha! So there you go. Okay, so check it out. That sphere is just kissing the YZ plane. And of course, where is the point of tangency? Bonus question. Where will we find the point of tangency? Well, we said that x should be 0. And what are the rest? Well, the y and the z should be the same as the center of the sphere, which would mean 1, 2. Yeah, there it is. Okay, so there is our point of tangency, where the sphere is tangent to the YZ plane. All right, so we saw a sphere, we've seen planes, and these two objects are examples of what are called surfaces. Okay, so what is a surface in general? For now, we will just say very loosely that it is a collection of points in Cartesian space where if you are at one of the points on the surface and you look around near you, it kind of looks like you're on a plane, okay, something flat, okay, or something that might almost be flat. Okay, so that's very, very rough definition. There is, of course, a more rigorous mathematical definition, but we'll basically just draw from our examples to give us some idea of what would a surface look like in general. Okay, how can we think of a function, a surface algebraically in terms of what are called functions? Okay, so here's an example of a Cartesian equation for a plane, and we can solve for z. Okay, so bring the x and y to the other side, divide everything by 4. Distribute if you want to. Okay, so what you see over here is an algebraic formula or expression that involves x and y. Okay, so that makes it a function on the two variables x and y. Okay, so we can write z as f of xy, give the function a name. Oh, f. How boring. Okay, and give a formula for it. In this case, 3 minus 1/2 x plus 3/4 y. Okay, when we talk about functions in basic algebra or in calculus, one of our first questions is usually, what's the domain? Okay, so in other words, what values can you replace x and y so that you can compute the function? Okay, which means an answer will come out, a value will come out. Okay, well, it looks like any number can be plugged into x and y over here because there's nothing stopping us from dividing x by 2, subtracting what we get, multiplying y by 3/4, adding what we get. So the domain for this function is every pair of real numbers x and y. You can also write that as R2. Okay, so for example, here are some computations you can make for this function. Okay, plug in 0, 0, you will get 3. Okay, these two terms go away. Right, plug in 6, 8, you will get 6, and so on. Okay, you know how to plug in numbers into a variable. Okay, you are simply doing that now for two variables. 6 goes into the x, 8 goes into the y. Okay. All right, so let's formulate this concept. A function of two variables written as f of xy is a formula or an algorithm or a rule that accepts as its inputs two numbers x and y and produces as its output a uniquely determined number z, which is f of xy. We define the set of all ordered pairs of values x, y that can be input into f to be the natural domain or simply the domain of f. We write it as dom of f, the domain of f, which is a subset of the Cartesian plane. So in our first example, it was the entire Cartesian plane, R2. Okay, there's nothing wrong with that. In fact, that's the best possible scenario. The set of all possible numbers z which are output by f is called the range of f, denoted by range of f, which is a subset of R, because it's just a single number. What are all the numbers you can output? That's a subset of the set of all real numbers. Okay, so let's might as well go through the rest of this example where we have a somewhat different function. Let me scoot up over here. We have g of xy, the square root of 25 minus x squared minus y squared. Okay, so that's very different now. Okay, we have a complication. We have a square root, right? And we know for a fact that you can only compute the square root of a positive number or 0. Okay, so whatever number you get in here needs to be at least 0. Okay, so can we plug in both zeros for x and y? Sure, you'll get square root of 25, which is 5. Okay, how about negative 1, 2? Okay, so you'll get 25 minus 1 minus 4, that's 20, still positive. Square root of 20, sure, it's irrational, but it's still a number. We don't discriminate. Okay, how about negative 3, 4? Okay, so now we are going to get 25 minus 9 minus 16. That's 0. Square root of 0 is, of course, 0. Okay, but what if we now input, let's say, 6 for x, 0 for y? So the y is not going to hurt you, but 25 minus 36, ooh, that's negative 11. Okay, so 6, 0 is not a valid input. 0, 6 is not a valid input either. We can switch it around. Okay, so what do we have to satisfy? All right, so I said it earlier. I said that 25 minus x squared minus y squared has to be at least 0. Let's go to our scientific notebook and play around with that. Okay, so here's our function, and we want the radicand, which is the expression inside our radical, to be at least 0. Okay, we want to satisfy this has to be greater than or equal to 0. Okay, I have a symbol palette that you don't see up here. Okay, so, well, what can we do with this? We can move x squared and y squared to the other side. So this inequality is equivalent to 25 has to be greater than or equal to x squared plus y squared. Okay, so that's nice. What's another way to write this inequality? So how about we put the x squared plus y squared on the left? Kind of just pivot it around. And so instead of greater than or equal to, we now should have less than or equal to 25. Ooh, we're back to basic algebra. Okay. If this were equal to 25, what were we just talking about? Circles and spheres. So if that were equal to 25, that would represent all the points on a circle centered at origin of radius 5. Okay, but there's a less than over here. Okay, there's a pesky less than or equal to. Okay, so what values of x and y will make that smaller than 25? We need to be inside the circle. Okay, so the domain, the natural domain of this function would be all the points on the circle, x squared plus y squared equals 25, and inside the circle. Okay, let's go to GeoGebra and check it out. All right, so we're actually back in 2 dimensions because GeoGebra can draw that inequality for us. Check it out. X squared plus y squared less than or equal to, so there is a less than or equal to there, 25. Ooh, there it is. Okay, so we call this the solid disk of radius 5, which is centered at the origin. Okay, so this is the domain of our function. All right, what is the graph of that function though? Okay, what do the points x, y, z, where z is square root of 25 minus x squared minus y squared, what will that look like in GeoGebra? Okay, so yeah, how about let's just go there. So let's go to 3 dimensions, view, 3D graphics. Okay, and we can hide our 2D because we do see it. We do see it over here in 3 dimensions. Okay, what does the graph of this function look like? Input square root 25 minus x squared, minus y, squared. It ain't over until we complete the formula. All right, well, what does that look like to you? Okay, it seems, oh, wait a minute, there's no bottom. It's almost looks like a sphere. Okay, maybe because it is a sphere. Except it's only the upper half. Okay, well, this should not be a surprise to you because we do this in algebra as well, in pre-calc. Okay, if you have x squared plus y squared equals 25, for example, let's forget about z. Okay, if you solve for y, you will get square root of 25 minus x squared. That will be the upper half of a circle. Okay, as a matter of fact, let's go back down to 2 dimensions. Okay, if you input square root of 25 minus x squared, there it is. Okay, we don't even have to go back down to 2 dimensions. That should be a familiar looking graph from algebra pre-calculus. that is the upper half of x squared plus y squared equals 25. Okay, so similarly, this function that we have is the upper half of the sphere x squared plus y squared plus z squared equals 25. Okay, same idea. Solve for z, you'll get square root of 25 minus x squared minus y squared. All right, let's do an example similar to what you would find in the handout right after that example that we just looked at. Okay, so it also has a logarithm, the natural logarithm. But let's put 6 minus 2x plus 3y inside the parentheses. Okay, so just like you can only take the square root of a positive number or 0, you can only take the logarithm of a number which is positive. Okay, 0 is not allowed anymore. ln of 0 is undefined. Okay, so we must force this number, 6 minus 2x plus 3y, to be greater than 0 this time. Okay, we must satisfy this inequality, right? So, what does that mean? Well, remember what we did to that last inequality. How about let's keep the left side, except for the 6. Let's move the 6 to the other side. Okay, like this. Okay, so there's nothing wrong with that. Okay, even though there are two minuses, who cares? Okay, well, remember though how we said if we had equals 25, we would be getting a circle in our last example. Okay, so similarly, if this were an equation instead of an inequality, if this were that equation, what does that look like? Okay, well, this would be a line, right? That's the general equation for a line. Okay, and in fact, its intercepts are, okay, as a matter of fact, I gave you a very nice equation. It's easy to see what the x and y intercepts of this line are. Okay, when x is 0, y has to be minus 2. Okay, and what happens when y is 0? X has to be positive 3. Okay, so yeah, let's use our imagination for a minute. Okay, we now know where the intercepts are: 0, minus 2 over here, and 3, 0 over here. Okay, so we have a line passing through those 2 points. Okay, however, that does not tell us, well, which points, x, y, will make this greater than minus 6. Okay, so if you remember back in algebra, you do a test point. Okay, and because this line doesn't pass through the origin, okay, we can test the origin. Test 0, 0. Okay, so if you plug in 0, 0 on the left, you just get 0 greater than minus 6. Okay, so does 0, 0 satisfy this inequality? Is 0 greater than minus 6? And the verdict is yes. Okay, so what did we learn in algebra? If one point on the side of this line satisfies the inequality, then every point which is on the same side of the line as that point will also satisfy the inequality. Okay, so we are now able to answer the first request. Find and describe the domain of this function. Okay, so thus the domain of H is the half plane which is above the line minus 2x plus 3y equals negative 6. Okay? So therefore, you can plug in any point which is above that line into our function, and you can compute the value of that function. Okay, so let me show you something else that Scientific Notebook can do. And for that, I'm going to magnify it a little bit so you can see it better. The better to see you with, my dear. So here's our function. Okay, and I'm going to put that function in a pair of braces. Okay, and what am I going to do? Okay, and let me make it actually even bigger. Okay, wow, that is really huge. Okay, so the nice thing about Scientific Notebook is that it lets you compute the function. Okay, all you have to do is put a subscript and put in the values that you want. Haha, plug in. How about x equals 0, y equals 0? Okay, and then I have an equals button here. Ooh, you get ln of 6. You want an approximation? There it is. Okay, so you can plug in 0, 0. Okay, so pick another point above that line. Okay, can you imagine it? Okay, pick any point. Oh, how about 1, 2? Okay, when x is 1 and y is 2. Okay, any problem with that? I don't think so. You'll get 6 here, 12 minus 2, 10. ln of 10? Yep, ln of 10. So that is valid. Okay, that is a valid point that we can plug in, and we will output approximately 2.3. Okay, how about the point below that line? Shall we dare? Okay, so we know that the y-intercept was, what was it again? -2. So if you plug in -3 for y and 0 for x, you're going to be in trouble because you're going to get 6 minus 9, -3. You can't find the value of ln of -3. What will Scientific Notebook do? Do I dare? Let me save the file, just in case. Ooh, what is that? Okay, so of course, that is the imaginary unit I. We have a complex or imaginary version of the ln function. Okay, so if that makes you wonder what it is, take a class called complex analysis. It is awesome. Okay, so let's go to GeoGebra and see what the graph of this function looks like. All right, so let's input that. ln of 6 minus 2x plus 3y. And, ooh, there it is. Okay, so check it out. It kind of, yeah, if you look at it this way, that does remind us of the ln function, doesn't it? Okay, the ln has a vertical asymptote. Okay, so in this case now, that vertical asymptote is going to be the line that we said we should be above off on the xy plane so that we can compute the value of that function. So as a matter of fact, let's rotate this way. Oh, here's the top view. Okay, the z-axis disappeared. That's when we know that we're straight above it. Okay, so that line should be over here. Okay, so let's try it. Minus 2x plus 3y equals -6. Ooh, except of course, that is no longer a line. That is, ooh, a plane. Okay, because we're in 3D mode. Okay, if you look at it in 2 dimensions, that is of course going to just be a line. Okay, so this is still a Cartesian equation for a plane. Okay, but it is parallel to the z-axis because there is no z value. The variable z does not appear in the equation. Okay, so that plane yeah, it's not going to intersect the z-axis like ever. Okay, so there you go. It does remind us a little bit of the ln function, okay? But of course, now it is a surface, right? And you can zoom out if you want to see more of it. You can do that. Let's drag it a little bit. Let's drag. Okay, ooh, there you go. Okay, so I get to see a little bit more of it. Okay, so yeah, that is our function. Okay, so we can of course go crazy. Okay, there are so many functions that we can play with. All right, all you have to do is look at the scientific calculator. And, you know, we got sine, cosine, tangent, ln, e to the x, okay? But even more basic, okay, let's put these away. Even more basic, we have polynomials, okay? So we know about 3x squared minus 5x plus 2. If you include a second variable, you still get what's called a polynomial, but now it's in two variables, okay? So what if we input 3x squared, there you are, 3x squared y, ooh, interesting, minus 5x y plus 2y squared. Ooh, all right. So is there any number that we're not allowed to plug in for x and y? I don't think so. Okay, the domain is still all of R2. Okay, but check it out. Look how crazy looking that graph is. Okay, and it looks like it's in two pieces, but no, it's not in two pieces. It's just because we're not seeing all of it that we seem to have these parts of that graph and they're disjointed. No. We know that a polynomial is continuous, okay? But if we only look at parts of a polynomial, it might look like, oh, wait, that's detached from the rest of the graph, okay? So here is one way that I cheat, because the scaling on x, y, and z is something we can't play around with in GeoGebra, okay? So what you can do is you can scale the function, the z values, manually by, let's say, dividing everything by 100, okay? So let's say you have b divided by 100, okay? GeoGebra knows who b is, so this will be what you get when you divide b by 100. And there's our graph, okay? So now let's hide the original function. There you go. Okay, so now it looks like it's more in one piece, okay? And, ooh, there's actually some symmetry going on here. It looks like it. Huh. Is it symmetric across the y-axis? Ooh, I don't know. All right, so, yeah, that is something that you might call a surface. It's not exactly flat, of course. Hardly any part of it is flat. Okay, but if you zoom in close enough, yeah, it might look like it could be flat. Okay, so yeah, we can certainly keep playing with this. What else can we do algebraically? You can divide a polynomial by another polynomial. Okay. So let's keep it simple, both in the numerator and the denominator. What if you had 2x minus 3y, and then we divide that by, ooh, how about x plus 4y? Ooh, okay, so, do we have any issues? Yeah, you're not allowed to divide by 0, right? So this time, the domain of our function is x plus 4y should not be 0. Okay, but if it were equal to 0, what you would get, again, would be a plane. Okay, so in the same way that when we set this equal to 0, we got a line in the xy plane. but in space, it's still a plane. Okay? So if we set the denominator to 0, okay, we get a plane in space. All right, right there. Ooh, and check it out. If you look this way, yeah, it does look like there's an asymptote going on there. Okay, if you remember from your basic calculus and pre-calculus, there seems to be an asymptote going on there. Okay, so once again, if you want to scale it a little bit, let's take d and divide by 100. Ooh, there we go. Okay, so yeah, now it's a little bit better. Okay, so yes, we get this graph. And this function is an example of what is called a rational function. You have a polynomial divided by another polynomial. Let me scoot over here. Okay, so we have a discontinuity. All right, you're not allowed to touch this line x plus 4y equal to 0. Okay, otherwise you will be dividing by 0. So the domain is all the points in R2 which are not on this line. You can be above that line, you can be below that line, but you cannot touch that line. Okay, so yeah, we get something which looks a little bit like an asymptote. I really love GeoGebra. Okay, you can make all of these beautiful pictures. I once told my friends that GeoGebra is like a musical instrument that plays music that you've heard in your head all this time, but you couldn't write down. Okay, well, it is now 37 minutes into the video. I was hoping to finish this handout, but there's still one big topic left, and that is quadric surfaces. So I'm going to take back what I said at the beginning. There will be one more video after this. Should have known I couldn't finish it in the time that I thought. What was I thinking? So, thank you so much for watching, and I'll see you for our 6th video where we talk about quadric surfaces. Enjoy the rest of your day. Bye.